In this episode, we consider the Schrödinger equation, the fundamental equation of quantum mechanics governing time evolution of a quantum particle. In a way, the Schrödinger equation in quantum mechanics plays the same role as Newton's law in classical mechanics, which defines the time evolution of a classical system. Consider the full time-dependent wave function, which we'll denote by capital Psi. Some hints on the time evolution of quantum system were given in episode 2. Schrödinger's insight was to consider a diffusion-like partial derivative equation, but with time derivative multiplied by imaginary factor I. This equation is called the time-dependent Schrödinger equation. For simplicity, we consider the time-independent potential of x. Let's try to solve it by separation of variables. Write capital Psi of x as a product of two functions, psi of x and phi of t. Here, the first part, psi, depends only on x, and second part depends only on time. Compute the derivatives and substitute them into time-dependent Schrödinger equation. Divide the left-hand side and the right-hand side by psi phi. Note that now the left-hand side depends only on t and the right-hand side depends only on x. And this can happen if and only if the left-hand side is constant and does not depend on t, and the right-hand side is the same constant, so it doesn't depend on x. Otherwise, we, for example, by changing t, could change the left-hand side, not touching the right-hand side, and break the equality. We denote this constant not by usual letter c, but rather by letter e. The reason for that will be clear in a minute. So, consider first the left-hand side. We can solve this ordinary differential equation by separating the variables. Integrating, we get this, and we find phi. Comparing this with the time-dependent wave function of plane wave, we can identify E as energy. This is the reason we have chosen the letter E for the separation constant. Now, let's consider the right-hand side. Multiplying both sides by psi, we get this. This equation is called time-independent or stationary Schrödinger equation. Let's dive into it a little bit deeper. Anyway, if we'll be able to solve it, then the full time-dependent Schrödinger equation will also be easily solved. First, note that if the potential equals 0, then our stationary Schrödinger equation simplifies and in fact can be easily solved. Two independent solutions are just familiar plane waves, e to the power plus ikx and e to the power minus ikx. Substituting any of these into the equation, we get this. So we find k. In the numerator, we have precisely the classical momentum of the particle. So the psi function can be written also in this way. So the complete time-dependent wave function is the following. So the solution of the Schrödinger equation tells us that a free particle propagates like a wave, and it leads to the wave-particle duality, where particle-like behavior can be reconstructed from the wave packets discussed in episode 2. Now, if the potential is not equal to 0, then the Schrödinger equation becomes much more complicated and cannot be solved for arbitrary u of x. Let's try to bring the equation in a simpler form. First, take psi out of the brackets. Recall the momentum operator from episode 4. Then this combination becomes p squared, meaning that we apply the momentum operator 2 times successively, one after another. For example, p squared acting on psi can be written in this way. Therefore, which tells us what is p operator squared. This means that the first term in the brackets can be written as p operator squared over 2m. If p was just ordinary classical momentum, then it would be just a classical expression for the kinetic energy. For p operator, it will be a kinetic energy operator. For the second term, since x operator is just operator of multiplication by x, then any function of it will be also a multiplication operator. Let's denote this by u operator. So here in brackets we have just the sum of kinetic and potential energies operators, which we'll denote by h. It is called Hamiltonian, which is actually the operator of the total energy. The Schrödinger equation can now be written in a simple and beautiful form. Looking at this minimalistic form of the Schrödinger equation, recall your linear algebra course, and you can immediately see that it resembles the eigenproblem for matrices. In the language of quantum mechanics, it states that you should find such psi functions that when acting on them by the Hamiltonian operator, you'll obtain exactly the same psi function, just multiplied by a factor, and this factor will give you the corresponding energy. So the solution is some particular state psi of n with the corresponding energies E of n. The set of energies can be discrete or continuous, or even can contain both discrete and continuous parts, depending on the potential. The important thing is that for a given potential, not every value of energy will correspond to a solution of the Schrödinger equation, and only some particular energies will give solutions. This allowed Schrödinger to naturally explain such a long-standing problem as energy quantization in atoms. The solutions of Schrödinger equation psi n are called the stationary states or orbitals. Let's discuss them a little bit more. Stationary Schrödinger equation allows to find the energy levels of the system En, at least in principle, and corresponding psi function psi n. If we can find En and psi n, which is usually a non-trivial task, then we can easily find phi of t and the corresponding full wave function, capital psi. Such solutions of the time-dependent Schrödinger equation are called stationary states. They are important for several reasons. First, observables in these states do not depend on time. This is because when we are calculating some observable, we always have a product of psi and psi star. We see that these time-dependent factors cancel, and we get time-independent result. This is the reason why these states are called stationary. Apart from the phase factor, nothing changes in these states with time. Second, these are states with a definite value of energy. This means that measuring energy in state psi n, we always get the same result, En. Linearity of the Schrödinger equation implies that if we have two solutions, adding them up, we get also a solution, which is called superposition of these two states. So, if we are lucky and can solve the stationary Schrödinger equation, then we get a set of stationary state solutions, which is a complete set. This means that any other solution can be written as a linear combination of these stationary state solutions. If at t equals 0 we have some linear combination of stationary states, then each stationary state psi n evolves independently in time. And at time t, we have this same linear combination. Let's conclude what we have done in the first week. We introduced the basic concept of quantum mechanics, such as the notion of wave packet. Then we considered wave function and its properties. We found the role of commutators of operators and their relation to Heisenberg inequality. And finally, we described the time evolution of wave function, which is governed by time-dependent Schrödinger equation, and derive from it stationary Schrödinger equation. In the next week, we'll explore further the Schrödinger equation and solve it for different important cases, such as infinite square well, delta function well and better, and for the harmonic oscillator. Don't forget about your homework, which will help you immensely to comprehend the ideas behind the course. So, good luck with your homework, stay tuned, and goodbye!